After 250 million years of vertebrate evolution pushing against every physical constraint available, the largest land animal that ever lived weighed about 70 tons. Godzilla weighs 90,000, and that gap right there is where biology ends and impossibility begins. For about 400 million years, evolution has been trying to build the biggest land animal it can, probing the limits, engineering around constraints, finding every trick available to carbon-based biology. The record, after all that time and all that pressure, is somewhere around 70 tons. Godzilla, in the 2014 film, weighs 90,000. That gap isn't a matter of degree, it's the difference between the edge of what physics allows and something that couldn't survive its own existence for 30 seconds. And understanding exactly why is one of the more beautiful things I've come across in biology. This isn't about nitpicking movies, it's about something genuinely beautiful, a mathematical law so fundamental that it shapes every living thing on this planet, from bacteria to blue whales, and draws a hard ceiling on how big a land animal can ever physically be. Cross that line, and the universe doesn't negotiate, doesn't bend the rules for something cool enough, and doesn't offer exceptions. It simply enforces what the geometry requires. What I want to show you is why giants are impossible, what would actually happen if one existed, and what the largest things that have ever lived tell us about where that ceiling actually sits. Because the ceiling is real, it has been hit before, and the story of how life keeps bumping into it is one of the most interesting things in all of biology.
There's a mathematical principle called the square-cube law, and once you see it everywhere. Take any object and scale it up uniformly. Double its height, double its width, double its depth. Its surface area increases by the square of that factor, so 4 times larger. But its volume, and therefore its mass, increases by the cube, so 8 times larger. That sounds abstract, so here's what it means in practice. Take a dog and scale it up to twice the height. Its bones, which have to support its weight, are cross-sections. They scale with surface area, making them 4 times stronger. But the weight they're holding is 8 times heavier, which means you've already created a structural mismatch just by doubling the size. Scale up 10 times, and the weight is 1,000 times greater, while the bone strength is only 100 times greater, leaving the structure catastrophically under-engineered for its own body. Galileo figured this out in 1638, not with computers, not with stress modeling, but with geometry and a quill. He wrote that if you tried to build a giant animal by simply scaling up a smaller one, the bones would have to be proportionally thicker, almost grotesquely so, just to compensate, and that at some point the bones become so massive they leave no room for muscle, organs, or anything else. The animal becomes essentially a solid mass of bone, and even then, the math still isn't satisfied. This is not a flaw in our current understanding waiting to be overturned, and it's not a simplification. It is a geometric fact that applies to every physical object in every universe with 3 spatial dimensions. There is no material strong enough, no evolutionary trick clever enough, and no fictional handwave sufficient to scale your way out of it. Applying this to Godzilla specifically is worth doing, because the numbers are stark enough to be clarifying. Godzilla in the 2014 film stands about 108 meters tall and is estimated at roughly 90,000 metric tons. For comparison, the largest land animal that has ever existed, Patagotitan maiarum, a titanosaur sauropod, stood about 6 meters at the shoulder, stretched 37 meters long, and weighed somewhere around 70 tons. That's the record, 70 tons on land, after 250 million years of vertebrate evolution probing the boundaries of the possible. Paleontologists can calculate from titanosaur bone geometry that those animals were already operating at near the maximum compressive stress that biological material can sustain, not comfortably within the limit, but pressed right up against it. Godzilla is 90,000 tons, which means his femur, the thigh bone, would need to be, by square-cube scaling, roughly as wide as it is long. What you'd get is a cylinder of bone that can't bend, can't articulate a joint, and can't attach any functional musculature, not a leg in any biological sense, but a structural pillar incapable of movement. And this is before accounting for dynamic loads, which are the forces generated during actual movement. Every step a bipedal animal takes sends a shockwave through its skeleton at multiples of its standing body weight. Humans hit about 1.2 times body weight walking, up to 3 times running. For a 90,000-ton animal moving at any speed, those transient forces would be measured in hundreds of millions of newtons per square meter, concentrated through joints, and bone fails at around 170 megapascals compressive stress. Godzilla's skeleton fails the moment he shifts his weight forward, not gradually, not over time, but in the first instant of attempted movement.
The skeleton is the most visible problem, but the biology underneath it is quieter and just as fatal. Your circulatory system works because your heart generates enough pressure to push blood from your feet to your brain against gravity, which for a human means overcoming about 1.2 meters of vertical distance. A giraffe, 5.8 meters tall, has a heart that weighs 11 kilograms and generates blood pressure roughly twice ours just to keep the brain supplied. And even then, giraffes have evolved special valves, elastic arteries, and a dense network of vascular modifications near the skull specifically to manage the pressure swings when they lower their head to drink. That is the most extreme mammalian cardiovascular system we know of, and it exists to solve a 5-meter height difference. Godzilla's brain sits roughly 100 meters above his heart, and the pressure required to push blood that high, even ignoring the sheer volume of blood and the diameter of the vessels required, would rupture every artery in his body long before it reached his skull. The heart required to generate that pressure would be larger than most buildings, would consume a staggering fraction of his total caloric intake just to beat, and would send shock waves through his own tissue with every contraction. Oxygen delivery adds another layer to the same problem. Lungs work through diffusion across a membrane, meaning oxygen passes from air into blood across a surface area that scales with the square, while metabolic demand scales with the volume, meaning the cube. A scaled-up animal needs proportionately less lung surface per unit of mass, which sounds like an advantage until you realize it means the lungs cannot keep pace with the body's oxygen demand at any sustainable respiratory rate. This is actually why insects can't get large. They abandoned lungs entirely in favor of air tubes running directly into tissues, which works beautifully up to the point where the diffusion distance gets too long and the system saturates. During the Carboniferous, when atmospheric oxygen sat at 35% instead of 21%, dragonflies reached 70 centimeters in wingspan because the atmosphere itself was the variable controlling their size ceiling. Under our current atmosphere, Godzilla would asphyxiate from the inside out before his cardiovascular system even had the chance to fail. Here's the constraint that almost never comes up in discussions of giant monsters, and it may be the strangest one. Every metabolic reaction that keeps an animal alive produces thermal energy as a byproduct, and the body sheds that heat through its skin, radiating and sweating across its surface area. Surface area scales with the square, and metabolic heat production scales with the cube, which creates a fundamental asymmetry that gets more severe the larger you go. This is why small animals have disproportionately high metabolic rates. A shrew has to eat almost continuously because its large surface-to-volume ratio bleeds heat so fast that stopping means dying of cold within hours. An elephant sits at the opposite extreme, with such a low surface-to-volume ratio that overheating becomes a serious physiological concern, which is why elephants evolved enormous ears, specifically as thermal radiators, vascularized sheets of skin to dump excess metabolic heat into the environment. Scale that problem up to Godzilla, and his surface-to-volume ratio is so low that even at a minimal resting metabolic rate, the heat he generates has essentially nowhere to go. His body would function as an insulated vessel with a continuous internal heat source and almost no means of dissipation. His core temperature would rise from the moment of his existence, not from any external source, but from his own biochemistry. And the atomic breath the films treat as his weapon is, in thermodynamic terms, adding an additional heat generation mechanism to an organism that is already a slow-motion thermal catastrophe.
The largest animals that have ever lived, blue whales at up to 190 tons, are aquatic specifically because water conducts heat away from the body roughly 25 times more efficiently than air does, making the ocean a passive cooling system. Without that, a blue whale on land overheats and suffocates under its own weight within hours, which illustrates that water doesn't make a giant animal truly viable. It simply postpones the same intersecting set of problems a little longer.
Evolution has been running this experiment for 500 million years, probing the boundaries of what physics permits over and over again. And the pattern in the results is coherent enough to be meaningful. Every time a land lineage pushed toward the size limit, it converged on the same set of engineering solutions. Sauropod dinosaurs, the Titanosaurs, Brachiosaurus, Argentinosaurus, developed hollow bones with internal struts and honeycombed air pockets that traded mass for volume while preserving structural integrity. Their necks were pneumatically supported by a system of air sacs connected to the lungs, making them dramatically lighter than solid tissue of the same volume would be. They kept 4 legs on the ground to distribute the load across the largest possible base, almost certainly ran slow metabolisms by warm-blooded vertebrate standards. And after all of that engineering, after 250 million years of refinement, they still topped out around 70-80 tons, not because evolution lost patience, but because the physics stopped giving. Marine giants got bigger by offloading gravity to the water, but hit their own limits in circulatory complexity and feeding efficiency. Blue whales filter feed on krill, the lowest possible position on the food chain, specifically because no predatory hunting strategy generates enough caloric return to fuel a 150-ton body. Flying animals hit a harder ceiling still. Quetzalcoatlus northropi, a pterosaur with an 11-meter wingspan and an estimated mass of around 250 kilograms, was likely already operating at or near the aerodynamic limit for powered flight, and analyses suggest it spent most of its airborne time soaring rather than flapping, because above that mass, powered flight becomes physically implausible on Earth's current gravity and atmospheric density.
A kaiju doesn't need a military to defeat it. It needs to exist for approximately 30 seconds. The skeleton collapses under its own weight before the first footstep completes. The cardiovascular system fails to supply the brain with oxygenated blood across a 100-meter vertical distance. The lungs suffocate the body faster than the muscles can move it, and the metabolic heat, with nowhere to go, cooks the whole structure from the inside. What kills the kaiju isn't a missile, it's the cube in square cube law, operating exactly as geometry requires. And that's not a depressing conclusion, because those same constraints shaped every living thing that has ever existed on this planet. The square cube law is why a shrew's heart beats 1,500 times per minute and a whale's beats 5. It's why sauropod bones look like aerospace engineering under a CT scanner. It's why insects breathe through holes in their sides. Physics isn't a limitation that life works around, it's the pressure that sculpted everything you've ever seen alive, the force that made evolution inventive, and the boundary that turned the history of size on Earth into one long, elegant negotiation between ambition and geometry. The giants were always going to be impossible, and the real miracle is how close evolution actually got. If you want to go deeper, how paleontologists calculate the weight limits of extinct animals from bone cross-sections, what a kaiju-scale organism would actually require in terms of atmospheric oxygen to breathe, or what the theoretical maximum size of a land animal would look like on a planet with half Earth's gravity, let me know in the comments, and send this one to whoever in your life has spent too much time defending Godzilla's honor. Take care, and I'll see you in the next one.